Acids and bases are among the most important electrolytes. They play a key role in many environmental, industrial, and biochemical applications. They tend to have characteristic physical and chemical properties that distinguish them from other electrolytes. Acids, for example, appear in many food products, especially citrus fruits such as lemon, and they tend to have a sour taste. Many of them are highly reactive and they should be handled with care. Bases can also be highly reactive, particularly with living tissue, and they should also be handled with care. They're soapy to touch due to a saponification reaction with the oils in our skin that produces soap. They also appear in some foodstuffs, such as red cabbage, and they tend to have a bitter taste. Acids can be loosely defined as substances that ionize in water to form H+ ions, or hydrogen ions. We've already seen how the molecular compound hydrogen chloride, which is a gas at room temperature and pressure, can be bubbled through water to produce HCl aqueous, or hydrochloric acid. And we know that hydrochloric acid is best represented as H+ ions and Cl- ions floating around in solution. The H+ ion is a hydrogen atom with its electron removed. So essentially it's a proton, and acids are sometimes referred to as proton donors. We can classify acids in a number of ways. One is to classify them as strong acids and weak acids. A strong acid is an acid that is a strong electrolyte, and hydrochloric acid is an example of that, and nitric acid is another example of that. Now, strong acids, like strong electrolytes, ionize or dissociate completely when they're dissolved in water. So effectively, they exist only in their ionic forms. There are 7 strong acids. There are only 7 of them, and it's worth knowing what they are. HCl, hydrochloric acid; HI, hydroiodic acid; HBr, hydrobromic acid. You've got nitric acid, HNO3, sulfuric acid, H2SO4, perchloric acid, HClO4, and chloric acid, HClO3. So they're the only 7 acids that are considered strong acids that completely dissociate when dissolved in water. Here's some applications of some of the more common acids. Hydrochloric acid, you may know, is the main digestive fluid in stomach acid. Nitric acid is a very strong corrosive oxidizing acid that's used for dissolving minerals and dissolving metals to get metal ions in solution. And sulfuric acid is the acid that's used in car batteries. Weak acids are acids that are also weak electrolytes. Acetic acid dissolves in water to form the H+ ion and the acetate ion, and it's a weak electrolyte because it doesn't fully dissociate. HF, hydrofluoric acid, is another example of a weak acid. Weak acids only ionize or dissociate partially, and you can see in both of these examples we've got arrows going in both directions indicating that as the molecule is dissociating into its ionic form, so too are the ions recombining to form the molecule, and so we don't have complete dissociation. So these are 2 examples of weak acids. Other examples, well, there's literally hundreds of organic acids, and the hydrofluoric acid is the acid, the inorganic acid, that is the most common weak acid. Some common examples here: acetic acid is the main component of vinegar. Ascorbic acid is vitamin C. Citric acid, as we said, the acidic component in citrus fruits, especially lemons. And hydrofluoric acid is used in the etching of glass. We can also classify acids in terms of them being monoprotic, diprotic, or triprotic. And monoprotic acids yield or donate only 1 H+ ion or hydrogen ion per acid molecule to the solution. So hydrochloric acid and nitric acid are both examples of monoprotic acids. They only yield 1 H+ ion when dissolved in solution. The charge on the corresponding anions is also 1-. Diprotic acids, they yield 2 H+ ions per acid molecule. And the classic example here is sulfuric acid, but also oxalic acid is an example. You can see that both of these acids yield 2 or donate 2 H plus ions to solution, and the corresponding anions have a 2 minus charge. And triprotic acids yield or donate 3 hydrogen ions per acid molecule, and the classic example here is phosphoric acid, H3PO4, which donates 3 hydrogen ions per acid molecule, and the corresponding charge on the counter anion there being a 3 minus charge. Now, bases are in some ways the opposite of acids. They react with or accept H plus ions. They're sometimes known as proton acceptors. And bases produce the hydroxide ion, the OH minus ion, when dissolved in water. And so obvious sources of bases include the group 1 metal hydroxide, lithium hydroxide, sodium hydroxide, potassium hydroxide, are all soluble in water. But also the heavier group 2 metal hydroxides, if we go back to our solubility rules, calcium hydroxide, strontium hydroxide and barium hydroxide are also soluble in water and are good sources of the hydroxide ion. So sodium hydroxide solid dissolved in water forms sodium hydroxide aqueous, and we know that it's a strong electrolyte. It's best represented as separate solvated sodium ions and separate hydroxide ions. And similarly, the group 2 hydroxides such as calcium hydroxide also producing the calcium 2 plus ion and 2 OH or hydroxide ions per formula unit there. Strong bases are bases that are strong electrolytes, and strong bases, like strong electrolytes, ionize or completely dissociate when they're dissolved in water, and 2 examples there are those soluble salts which end up being strong electrolytes, sodium hydroxide and calcium hydroxide. So all of the soluble hydroxides, group 1 metal hydroxides and the heavier group 2 metal hydroxides would be classified as strong bases. A couple of examples here: sodium hydroxide, it's Drano, it's used as a drain cleaner and used as an oven cleaner. Calcium hydroxide, otherwise known as slaked lime, used in mortar for bricklaying. We have weak bases as well. Weak bases are bases that are weak electrolytes, and some molecules can actually produce the hydroxide ion when dissolved. And we have an example here: ammonia, when it's dissolved in water, produces the ammonium ion and the OH minus hydroxide ion. Now, this particular process is actually a chemical process. So when ammonia is dissolved in water, it produces the hydroxide ion and is said to be a base because it produces that source of hydroxide ions. You can see here, however, that this particular process is significant in both directions. So as ammonia is reacting with water to produce ammonium and the hydroxide ions, so too are the ammonium ion and the hydroxide ion reacting to produce the ammonia molecule back, as well as the water molecule. And so we don't have complete dissociation or complete ionization here. So weak bases only ionize or dissociate partially to form the hydroxide ion. So molecular compounds that produce OH minus ions when dissolved, ammonia is one example there, and pyridine is another. We use ammonia in household cleaners, and pyridine is used as a precursor for pesticide synthesis. So acids and bases classified as weak acids, strong acids, weak bases, strong bases. Acids can also be classified in terms of monoprotic, diprotic and triprotic acids.